Distribution of objects into groups or persons. Find the number of ways in which 6 different objects can be divided into, first bit, 2 groups with 2 and 4 objects respectively. Second bit, two persons with 2 and 4 objects respectively. Third bit, to the 2 groups with 3 objects each. Fourth bit, to the 2 persons with 3 objects each. Here, instead of writing the answer directly in terms of C notation or P notation, because we are having 6 different objects, let us consider those objects as A, B, C, D, E, F, and divide this into the 2 groups and list all the possible cases. Let us distribute the objects A, B, C, D, E, F into the 2 groups. So if I take to the first group A, B, then the remaining objects C, D, E, F will be in the second group. Like that, if AC is in the first group, then B, D, E, F will be in the second group. So if I go on write all possibilities, then there will be 15 possibilities will be there. That means the answer will be 15. Now, instead of listing this, we can write directly also. There are total 6 objects are the different objects, and to distribute to 2 and 4. I can distribute to the first group 2 and the next group 4. That means number of ways of distributing 2 objects from 6 is 62, and the remaining objects are 4, and we have to distribute to the 4 objects only. So 62 into 4C4. In terms of factorial notation is 6 factorial upon 2 factorial 4 factorial into 4 factorial upon 4 factorial into 0 factorial. Now if I simplify this, I can rewrite as 6 factorial upon 2 factorial into 4 factorial. Now this number I can correlate to the given problem as numerator corresponds to the total number of objects and the denominator corresponds to the number which the group contains the number of objects. So one group contains 2 objects, another group contains 4 objects. So for the second bit, to the 2 persons with 2 and 4 objects. Now, so the distribution will be, if I take 2 objects for the first person AB, the 4 objects C, D, E, F to the second person. Now here, one division is AB and C, D, E, F, and it can be interchanged also. That means the first person can get C, D, E, F, and second person can be AB also. That means for each division, you can have here interchanging also will be there. That means total here 15 into 2, so it becomes 30. Now in terms of notation, we can write as 62 into 4C4 into 2 factorial. This 2 factorial corresponds to the interchanging of the objects between the 2 persons. There is like 2 persons are there, so among themselves you can arrange in the terms of 2 factorial. That means everything will be same like in the first problem. It is 6 factorial upon 2 factorial 4 factorial into 2 factorial because the persons are different. So if you simplify, the answer will be 30. So in case of third problem, division of 6 different objects to the 2 groups with 3 objects each. That means if I group the first one as ABC, then the second group will be DEF. Now one group as ABC, another group as DEF. Also, when DEF also is here and ABC will be here. That means I cannot say that ABC, DEF and DEF, ABC are 2 different ways of distribution. It will be considered as the same. That means total cases will be what? Here 20, but in that 20, ABC, DEF and DEF, ABC will be considered as 1 only. So it will be half of the entire total cases. So that means the answer will be 10. Now in terms of notation, 3 objects have to distribute, give to the first group from 6. That means 6C3 into remaining objects are 3. So 3C3 into 1 upon 2 factorial. Why? Because this entire quantity and this entire quantity is same. It is like when we are discussing the problems of arrangement of the letters in a word. If repetition is there, so we are writing the denominator. Like that here, this quantity and this quantity exactly matches. So that's why we are writing as 1 upon 2 factorial. In the fourth problem, so to the 2 persons with 3 objects each, that means again the possible cases will be what? Like A, B, C, D, E, F, A, B, D, C, E, F, and so on. So 20 cases only will be there. Now because the persons are different, so here getting a one division is A, B, C, D, E, F, and D, E, F, A, B, C will be considered as a 2 different ways of distribution. That is 6C3 into 3C3 into 1 upon 2 factorial into 2 factorial. So this 2 factorial corresponds to the arrangement among the persons. So the value will become 20. So the another problem is consider 5 balls and 3 boxes. In how many ways balls can be distributed into the boxes so that in that first bit, balls identical and boxes are also identical. In this A bit, box can be empty. Second bit, no box is empty. That means you are distributing the 5 balls into 3 boxes. The balls are identical and boxes are also identical. That means you cannot differentiate from one box to the other box, and you cannot differentiate one ball to the another ball. And the distribution can have 2 ways. That is, one possibility is what box can be empty or no box is empty. So how many ways it will be there for the A bit as well as for the B bit. Now because the balls are identical, so we can use the symbols A, 5 times you can use it. And when boxes are also identical, you can use the symbol B, 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 and try to list the cases and then write the answer. So let us denote the balls as symbols A, 5 times, and boxes are identical. I am denoting as B, B, B. Now this balls I am putting into the boxes. Now there is a one possible cases, all the balls I can put it in the one of the box. So I am denoting this as A to the power of 5. The meaning of this is 5 balls under this box and 0 in the second and third box. Now whether I keep 5 balls in the first box or second box or third box, there is no variation. Why? Because boxes looks identical. Next, another case is 4 balls in the one of the box and 1 ball in the another box and 0. Here also, whether it is A power 4, A0 or A to the power of 4, 0A, there is no variation because the boxes are identical. Third case is 3 balls in one of the box, 2 balls in another box and 0. 3 balls, 1 ball, 1 ball, 2 balls, 2 balls and 1 ball. So total number of cases is 5. That means the first bit is box can be empty. So the answer will be 5. Second bit, that is no box is empty. That means you have to consider only these 2 cases. So that's why the answer is 2. So for the same problem, second bit is if the balls are identical and boxes are distinct, then how many ways 5 balls can be distributed into 3 boxes such that box can be empty and no box is empty. Now here balls are identical, so we are using the same symbol A 5 times. And because boxes are distinct, we are using the symbols B1, B2, B3. That means you can have a differentiation between from first box to the second box to the third box. So one possible case is all the 5 balls can be under first box and second box can be empty, third box can be empty, and these can be arranged among themselves in 3 factorial ways, and because 2 are same, so it will be 2 factorial. That means A to the power of 5, that is 5 balls, 0, 0, or 0 ball, 0, 5, 0, 0, 5, 0, next 0, 0, 5. That's why the value will be 3. Next, another possible case is 4 balls, 1 ball, and 0 ball, and among themselves you can arrange as 3 factorial ways. Next, 3 balls, 2 balls, no ball. Arrangement will be 3 factorial. 3 balls, 1 ball, 1 ball. So only 3 ways we can arrange, that is 3 factorial upon 2 factorial. 2 balls, and 1 ball. That means here also repetition is there. So 3 factorial upon 2 factorial, which is 3. That means when box can be empty, the number of ways is 21 total. and no box is empty means last two cases, that is 6. So another way of explanation for this is I can place all the identical balls in a row, and when I want to distribute into 3 boxes means I can use the 2 sticks and place it anywhere. That means I can keep the stick either before the first ball or between the first and second or anywhere, or second stick also I can keep it anywhere. That means just 2 sticks I am placing in between the 5 balls. Now it is like this looks like a letter. Now the arrangement of these letters, total number of letters I can say as 7. So 7 factorial. In this all are same, so 5 factorial, and these 2 sticks also identical, 2 factorial. So that value will be 21. That is for the first box can be empty. Because the meaning of box can be empty means this stick can be kept before the first ball. That means this is one box contains, second box contains, third box contains. Now, suppose if the no box is empty, then I cannot keep the stick before the first ball, or I cannot keep the second stick after the last ball. That means all these 2 sticks I have to keep in between. That means in between means because 5 balls are there, in between only 4 gaps will be available. That means I have to choose 2 places among 4. That means number of ways of choosing 2 among 4 is 4 C2, which is 6. That will be for the case of no box is empty. Now under the same problem, third bit. So distribution of 5 balls into 3 boxes such that balls is distinct and boxes are identical. In that A bit is box can be empty and no box is empty. Now here, because the balls are distinct, use the symbols as A, B, C, D, E, and boxes are identical, use the symbol B, B, B. And again list the cases, and after listing the cases, check in each case what can be the arrangements are possible, and then calculate the value when box can be empty and when no box is empty. So here balls we can consider as A, B, C, D, E, and because boxes are same, so I can consider as B, B, B. It is like you are dividing 5 different balls into 3 groups. That means all the 5 balls can be kept in one box and 0, 0. That means the number of ways is 5 factorial upon 5 factorial, which is 1. That means whether I kept all the 5 balls in the first box or second box or third box, it will be the same only. So there is no variation because in the boxes. Next, second case will be 4 balls and 1 ball and no ball. That means this can be written as 5 factorial upon 4 factorial into 1 factorial. Like previously we have discussed distribution of different balls into groups. That is numerator corresponds to the total and the denominator corresponds to each box, each group contain how many. So 4, 1 and 0. So 4 factorial and 1 factorial, which is 5. Next, third case will be what? 3, 2 and 0. That means 5 factorial upon 3 factorial into 2 factorial. Next, 3, 1, 1. That means 5 factorial upon 3 factorial into 1 factorial into 1 factorial. Because the 2 groups, that is 2 boxes contain the same number. So again we are write into 1 upon 2 factorial. Next, 2, 2, 1. That is 5 factorial upon 2 factorial, 2 factorial, 1 factorial. Again 2 boxes or 2 groups contain the same number. We are write as 1 upon 2 factorial. So the total when you add, it will be 41. So box can be empty, answer will be 41, and no box is empty will be 25. That is last 2 cases. So the fourth problem is if the balls are distinct and boxes are distinct, then in how many ways 5 balls can be distributed into 3 bars such that box can be empty and no box is empty. Because the balls are distinct, we can use the symbols A, B, C, D, E, and boxes are also distinct like B1, B2, B3. Even here we can consider as 3 different persons, because the distinct means there is a variation between the boxes. So instead of boxes, even I can consider person 1, person 2 and person 3. Again list the cases to the box wise and check arrangement among themselves. So in the fourth bit, balls are distinct and boxes are also distinct. Then we can consider, because balls are distinct, 5 balls, and boxes are distinct, we can denote B1, B2, B3, or you can say 3 different persons. Now again, balls can be distributed in one possible case is 5, 0, 0. That means 5 factorial upon 5 factorial into 1 upon 2 factorial. Why? Because two persons have the same number 0, 0, 1 upon 2 factorial, and arrangement among the persons will be 3 factorial. Next, second case is 4, 1, 0. So 5 factorial upon 4 factorial, 1 factorial, and arrangement among the boxes is 3 factorial. Next, third case is 3, 2, 0. Next, 3, 1, 1. That means again 5 factorial upon 3 factorial, 1 factorial, 1 factorial, because these two are contain the same number. So 1 upon 2 factorial, and arrangement among themselves is 3 factorial. 2, 2, 1. Again same as the previous case. 5 factorial upon 2 factorial, 2 factorial, 1 factorial into 1 upon 2 factorial, because these two contain the same number. And 3 factorial corresponds to, because the boxes are different, arrangement among themselves. So the total will be 243. And for the B bit, no boxes empty, means last two cases 150.
Sir, for that last case.
So when box can be empty, this also can be another explanation is like number of functions from set A to set B. Set A contains 5 elements and set B contains 3 elements. That the first element can be assigned to any of the 3 elements. Second element also can be assigned to any of the 3. Third also can be assigned to any of the 3. Fourth and fifth. That is 3 into 3 into 3 into 5 times. So 3 to the power of 5. Whereas the second bit corresponds to number of onto functions.